The topic of Lesson 8 is to analyze the deformation of a beam based on loads which are not external. For instance, let's see how a beam deflects based on its own weight. So basically, if you have a beam like this hanging downwards from the ceiling, it should go straight, and the only load which is applied to this beam is its own weight from the center of mass, let's say W. We want to see how this beam deforms uh, by its own load by its own weight applied to the beam in ANSYS. So this is the first case we're going to examine in this lesson. In the second case of this lesson, I'm going to have the same beam and I'm going to let the weight be applied to it. So the weight is there. Plus I'm going to apply some temperature difference to the beam. So I will have two cases to study in this example. So when it comes to applying weight or analyzing the deformation of a beam based on its own weight and temperature differences, what we have to do in ANSYS is to define two other material properties except for elasticity and Poisson's ratio. Again, I'm going to use steel as the material for this analysis, for which we know that elasticity is 200 gigapascals and Poisson's ratio is almost 0.3. But then, because I'm going with weight, and what I define will be a volume, in order to get the mass to analyze the effect of its weight, I'm going to apply density. For steel, it's almost 7,800 kilograms per cubic meters, the density of steel. And because I'm going to also examine the effects of temperature on this beam, I'm going to need to provide ANSYS with coefficient of thermal expansion alpha, which is for steel I've read to be 13 times 10 to the minus 6. So in this analysis, when I'm defining the material for my model, I'm going to give four values for my material: elasticity, Poisson's ratio, density, and coefficient of thermal expansion. And since I'm interested in the effect of weight, what I should be careful is the volume of the beam that I'm defining in my model. So I'm going to use beam 3 again as the element I'm going to pick for my analysis. And if you remember from previous examples, for beam 3 I have to give a real constant, for which it asks me for cross-section area and area, moment of inertia, and also some height. So the cross-section area of my beam is going to be what I have done before, 12 by 12, which gives me the cross-section area is going to be 144. IZZ is going to be 12 to the 3, and height is going to be 12 still. And I'm going to give a height of 300 millimeters, let's say, to this beam, to the steel beam. So these are all going to be in millimeters. You know that IZZ has a unit of length to the 4, and so height is going to be in millimeter. The temperature that I'm going to apply, the temperature difference I'm going to apply for this element, for this model, is going to be, let's say, 30. It's going to be 30, and I'm going to assume the gravity is going to be 9.8 meters per square second. This is going to be x direction, and this is going to be my Y direction. So I guess everything is explained. So let's switch to ANSYS and do the analysis. Alright, we are in ANSYS and let's run the analysis. The first step I'm going to do is to come to Preferences and make sure that I'm picking Structural. Click OK. Come to Preprocessor, and again, like always, define the element that I'm going to use. Go to Beam, and I'm going to pick Beam 3. Stick to the default options, click OK, and close the window, and come to Real Constants to define the cross-section area and the other requirements of this analysis, like always. OK, close the window, and I go to Material Properties, load Material Models. So one thing that differs in here compared to the previous 6 lessons is after I pick or define elasticity of 200 gigapascals and Poisson's ratio of 0.3 and OK the window, then I have to define a density. So I double click on density, give the density of 7800 for the material, and I come to thermal expansion, instantaneous coefficient, isotropic, and pick again 13 times 10 to the minus 6, and OK this window. So for material model number 1, I have defined density and the mechanical properties in terms of Poisson's ratio and elasticity, and also instantaneous thermal expansion coefficient. So while I was defining all of them, they were recorded for my material model number 1, so it doesn't mean that I have 3 different materials defined on my analysis. Perhaps if I were supposed to have more than one material for this analysis, I would come to Material, New Model, and it would add a new model here for me, and I could again provide it with different properties. But since in this example I'm only doing one material, so I'm going to stick with one model and close this window. Come to modeling. In contrast to what I did in lesson 6, in this lesson I'm going to generate my model by defining key points and provide the coordinates of 0 and 0, apply, and the next key point is going to be at a y of 300. Okay, so I have the beginning and the end of my beam, and then go to line, create lines, straight line, and pick the 2 key points and OK the window. And because I did my model or defined my model using key points and lines, I need to do meshing in here. The reason I did this is that I want to divide my model or my beam into 50 segments, so that I will have 50 or 51 nodes, and for each node I can read the displacement in y direction. If you remember in lesson 6, I divided my element or my model into 4 sections or 3 sections by defining 4 nodes. I could do that here too if I wanted, but since I want to divide my beam into 50 sections, it's more convenient to do a model like this, define the key points and generate a line between them, and come to mesh, come to size control and manual size, lines, and pick lines. I can say pick all because I only have one line, so I can either click that, and I'll come to here, number of element divisions. I'm going to pick, or I'm going to put 50. So my line is divided into 50 different segments or smaller segments. Then the next step is to come to mesh, lines, pick the line and click OK. Now my beam is divided into 50 smaller elements. My model is ready, so I come to load, and again I want to make sure that I'm doing a static analysis. Come to define loads, and the first thing I want to do is to make sure that on this end the beam is fixed. So I come to apply, structural, displacement on key points and click OK. All DOF all degrees of freedom are equal to 0. So I click OK this one. The constraint is applied, but I'm not applying an external load. Instead, I'm going to see the deformation of the beam according to its own weight. So I come to inertia, gravity, and global, and I want to see, if you see in this window, you can provide or you can input different values of gravity in X, Y, and Z directions, but I want to pick only in Y direction, and the gravity is going to be 9.8. I OK this window, and the other thing I want to mention in here is that despite my Y direction is upwards, but you don't give minus 9.8 for gravity in Y direction just to make sure that you're that everything is going downwards or the gravity is downwards. Perhaps when you give a value of 9.8, positive value of 9.8, everything is going to work the way we expect, and the material is going to deform downwards. So I click OK on this one, and so my model is ready. Go to Solution, Solve, Current LS, OK the window, the material is, or the analysis is done. So I go to General Post Process, and the first thing I want to see is nodal solution and a displacement in Y direction. So as you see, the displacement is in negative direction, or negative orientation in Y direction, which means despite I entered a gravity of positive 9.8, my material is expanding in the negative direction according to Y coordinate. I can also read stress in Y direction. Click OK. A constant stress of 0.017, probably megapascals or Newton per millimeter squared, is defined or calculated for this model. But let's see the reaction solution. All items, and the only node or the only end of this beam that has reaction is this top beam where we fixed it. And there is only one reaction, the Fy. So basically the weight of the material is in Y direction, and so the only reaction that we have in this end is Fy of 0.33 times 10 to the 10 newtons. We can also see nodal solutions, let's say Y component of deformation. So you can see the deformation for all of the 50 nodes that are, or 51 nodes that are in this model. Node 1, node 2 is 0, basically because node 1 is this end and node 2 is the other end. And the rest of the nodes have their associated values of displacement in Y direction. And we can also read stress in Y direction for each node in here. Which is only for, I guess, node 2, because we're only given one value or for one node. So basically that's what we read. Now let's go back and apply a second load to this model, and that is temperature. So I come to define loads, temperature on elements, and I want to define this temperature to all the elements. So I pick all, and for all of them I just pick or enter 30, 30, and 30, and I OK this window. Or okay, this one was wrong, so let's delete this temperature from all elements. The error that I saw was telling me that I have applied the displacement on a key point, which is not a node or an element. So basically, in order to properly do this analysis, I have to apply the temperature on line instead of on elements. So I come to apply structural temperature on lines and pick the only line that I have defined in this model and give a temperature of 30. Okay, so I don't see that error anymore. Come to solve, current ls. Okay, the window and the solution is done. Now let's see how my material deforms based on this heat and weight. So if you recall from the previous example, the deformation in y direction is a little bit larger than without the temperature. I can also see the stress in y direction. It's again greater than the temperature that we read for, or the stress that we read for weight only. I can also come to list results, reaction solution, and see the forces. Basically, the load that we see on Fy is kind of the same, probably because the temperature did not apply that much thermal stress on the material or the model. And the other thing I want to teach in this lesson is to see the 3D image of this analysis. So if you come to plot controls, styles, size and shape, and in front of display of element, okay this option, or check this option and click OK, you see a 3D representation of the analysis. And let's plot results, and again nodal solution and y. You see the same thing that we saw, but in a 3D representation. And let's see stress in y direction. It's all the same. Stress in x direction, we have some stress in x direction. But I want to point your attention to this case. In this 3D representation, the conservation of volume or mass is not really represented correctly, because according to the conservation of mass, as this beam expands in y direction, it should shrink in its area. But this model is not showing that thing. The best way, or the other way to do this analysis, is to define a 3D model from the beginning. So let's define a cube and a cube of the same cross-section area and the same height, and then apply the same loading conditions in terms of weight and temperature, and we will see that in the next lesson how the expansion of the beam in y direction according to its own weight and the temperature that is applied to it will change the cross-sectional area of each point at this beam. But before concluding this lesson, let's go to list results again, nodal solution, and see displacement in y direction. So again, displacements for each of the elements in y direction is shown to me, and I have 51 nodes, so I get 51 values that I can use to plot this in Excel, so I can read those displacements from here and list nodes, coordinates only. Okay, so I can read these values from here, save the two files, and merge them together and get one single Excel file and plot y versus displacement in y direction in Excel. With this, I'm going to conclude lesson 7.